Model physics. Model physics describe the processes unresolved by the model grid, radiation, cloud microphysics and surface processes. The processes described by the model physics are said to be parameterized, Pelkey, 2002. The subgrid scale and diabatic processes are parameterized so their contribution to the changes in the large-scale state of the atmosphere can be considered. The convective processes redistribute momentum, heat and moisture in the vertical. The deep convection parameterization, Fig 6, used in ALADIN, Girard and Geleyn, 2005, is a prognostic mass flux scheme, Girard, 2007, where convective processes are treated with the use of prognostic variables for updraft and downdraft vertical velocities and mesh fractions, Girard et al., 2009. Cloud microphysics describe the processes of condensation, evaporation, freezing and melting as well as the processes that transform the cloud water droplets and ice crystals into rain and snow, Fig 6. ALADIN uses a simple microphysics scheme with prognostic cloud water and ice, rain and snow, Khatri et al., 2007, and a statistical approach for sedimentation of precipitation, Geleyn et al., 2008. The microphysics scheme of the resolved processes is kept as close as possible to the original scheme that was without the prognostic condensates. The original scheme is the Kessler, 1969, type scheme with modifications, Geleyn et al., 1994, that include melting and freezing and imposing a brutal transition from ice to water at the temperature triple point. The radiation processes described in the model encompass the transfer, scattering, absorption and reflection of the shortwave solar radiation and longwave thermal radiation of the Earth's surface in clouds. There are several radiation schemes available in the ALADIN model, Morkret, 1989, Lahr et al., 1997, but the simplest one is used in the operational version. The operational scheme, Ritter and Geleyn 1992, is based on Geleyn and Hollingsworth, 1979, scheme. It is simple and computationally cheap since it uses only one spectral band for longwave and one for shortwave radiation computations. The scheme has been enhanced recently, Geleyn et al. 2005a, 2005b, but these modifications did not improve the cloud and temperature forecast in the stratus and fog case, Tudor, 2010. Schematic view of the scheme of the prognostic variables describing microphysics and convection and associated processes in the version of the ALADIN model used in CMHS. The turbulence parameterization scheme describes the impact of the unresolved motion and surface roughness on the vertical transfer of heat, momentum and moisture. The turbulent exchange coefficients are modified from Louis et al. 1982, and are computed using prognostic values of TKE, turbulent kinetic energy, according to Geleyn et al. 2006, and Redl-Sperger et al. 2001. The gravity wave drag and lift parameterization scheme describes the vertical momentum flux due to the atmospheric waves generated by the unresolved topographic features. The surface parameterization schemes describe the soil properties and their impact on the meteorological model variables. ISBA, Interaction Soil Biosphere Atmosphere, is the surface scheme used in the operational forecast, Norlin and Plantone, 1989, as well as in the surface data assimilation, Giard and Basile, 2000. The scheme describes the exchange of heat and moisture between land surface and air using thermal and hydrological properties of particular soil types, described with dominant land use type, percentages of clay, sand and silt, useful soil depth, thermal roughness length, and vegetation changes during the year, described by vegetation fraction, leaf area index, surface resistance to evapotranspiration. The prognostic variables are temperature, liquid and solid water contents are computed on two layers representing the soil surface and deep soil properties, and additional variables describe surface snow reservoir, density and albedo and ice and water on leaves. Snow budget depends on snow precipitation, evaporation and melting as well as snow accumulated on vegetation. Each parameterization scheme obtains the information on the state of the atmosphere from the model variables and possibly output from other parameterizations. Then it uses a set of closure assumptions that relate the parameterized process to the state of the atmosphere. The parameterization schemes have the largest impact on the prediction of the sensible weather at the Earth's surface, Pelkey, 2002. These schemes became more complex over time and interact with each other, the numerical and dynamical parts of the model. Model diagnostics produces the numerical values of the sensible weather fields from the model variables, such as the accumulated precipitation, instantaneous cloudiness or maximum wind gusts. Wind, temperature and humidity are interpolated from the model levels to the standard meteorological measurement heights, 10 and 2 meters above surface, using a parameterized profile, Geleyn, 1988.